students, my name is Lavanya Krishna. I am your physics educator for grade 10. Today we'll be talking about a new chapter, magnetic effects of electric current. Before we study this chapter, let's recall what we have studied in our previous classes. We have studied what a magnet is. It is a natural material which has the ability to attract or repel other magnetic substances, and also the poles. The magnet has the north pole and the south pole, and these poles can never be separated. That is, the monopoles never exist, and also like poles repel each other and unlike poles attract each other. Knowing about these magnets, let's start our chapter, magnetic effects of electric current. So what is magnetic field? To define it, let's consider a bar magnet and a current carrying conductor. The space or the region around the magnet or a current carrying conductor which is experienced by other magnetic substances is called magnetic field. That is, when I get a magnet, there is magnetic field around this bar magnet and there is magnetic field around this current carrying conductor too. So when I get a magnet near it, there is some kind of attraction or repulsion. That is due to the presence of the magnetic field around the bar magnet. The same scenario when I get a bar magnet near the current carrying conductor. It can either be attracted or it can be repelled. So, the region around it is called as magnetic field. Now, understanding what magnetic field is, let's study a little bit more about it. A magnetic field is a vector quantity, which means it needs complete specification of magnitude and direction. Which means we all know a physical quantity which requires both magnitude and direction is called a vector quantity. So what is the direction of this magnetic field? How do you find out the direction of this magnetic field? The direction of the magnetic field at any point is given by the tangent drawn to that point. Now let's consider a bar magnet and the field lines around it. We all know outside the magnet it starts from the north pole and ends at the south pole. So if I have to know the direction at any two given points, A, B, it is given by the tangent drawn to that point. And also let's consider two more points. The tangent drawn at this point will give you the direction of the magnetic field at that point. Now that we understood about magnetic field and how is the direction of the magnetic field, let's move on to understand the units of magnetic field. Now that we understood what magnetic field is, let's move on to study the units of magnetic field intensity. We all know there are two kinds of unit, the SI unit and the CGS unit. The SI unit being very important. The SI unit of magnetic field intensity is named after a very famous scientist, Nikola Tesla, which is Tesla. And it is denoted by the letter capital T. And the other unit which can be used instead of Tesla is Weber per meter square. This is the SI unit. And the CGS unit for magnetic field intensity is given by Gauss. And the CGS unit is also named after a German scientist. Now let's establish the relationship between the SI unit, which is Tesla, and the CGS unit, which is Gauss, which can be written as 1 Tesla is equal to 10 to the power 4 Gauss, or 1 T is equal to 10 to the power 4 G. Now that we understood this, let's move on to study our next topic, properties of magnetic field. So what are the properties of magnetic field? The first property is they are always closed loops. That is, so the correct way to draw a magnetic field is this, but this is wrong because the magnetic field line should never be discontinuous. It should be always continuous closed loops. Now, the next property, the lines start from the North Pole and end at the South Pole outside the magnet. That is, outside the magnet they start from North, end at South. But remember, inside the magnet, they start from the South Pole and end at the North Pole. And the third property being very important, the magnetic field lines never cross each other. So why shouldn't they cross each other? Let me show you a diagram. These are the two magnetic field lines that I've considered, A and B. And they tend to meet at point C. That is, they are crossing each other. Now, the direction at that point is given by the tangent 1 and 2. The point C has two tangents. You can never draw two tangents at one point. For example, if you are in the middle of the road, you can either take a left or you can take a right. You cannot take a right and a left simultaneously. And also, the other logical thing is, when I keep a magnetic compass at C, it can deflect in only one direction. It cannot deflect in two directions. So, two magnetic field lines should never cross each other. And the next property is, the density of lines is directly proportional to the strength of the magnetic field, which means more the magnetic field lines, stronger the field, lesser the field lines, weaker the field. If you want to represent the field is stronger, you can draw more number of field lines. If you want to represent if the field is weaker, you can represent with fewer field lines. Now that we understood the properties of magnetic field, let's move on to our next topic, that is magnetic effects of electric current. This is one of the most important topic in this chapter. Let's see what it is. To talk in a simpler way, the current carrying conductor produces magnetic field, and this is called as magnetic effects of electric current. To explain it more clearly, let me consider a conductor AB, which is carrying current from A to B, and let me place a magnetic compass right below it. So, whenever there is a flow of current in the conductor, the magnetic compass deflects. Deflects because, why does it deflect? That is because the presence of the magnetic field around it. This entire phenomenon is nothing but magnetic effects of electric current. But why do we need to study this? Because these deflections give, or these magnetic field gives rise to mechanical forces. And these mechanical forces are in turn used in various electrical equipments, in electric motors, electric generators. We all know the electric motors are again used in electric fans, electric mixers, etc. So it is very important to study about this chapter and this topic especially. And this was discovered in 1820 by a scientist, Christian Ørsted. Now that we understood what is magnetic effects of electric current, it is the magnetic field that is produced due to the flow of current in the conductor. Let's move on to study our next topic, Ampere swimming rule. Why do we need Ampere swimming rule? When the compass deflects, we all studied in our previous slide that when the current flows from A to B, there is a deflection. There is a deflection. So, in what direction does this deflect? To explain this, the law was given by Ampere's swimming rule. And this states that imagine a person swimming along the conductor in the direction of the current. Place a magnetic compass near or below him, and his left hand will deflect towards the north pole of the magnetic needle. That is, imagine a person swimming and the magnetic compass is just kept right below him, and he is swimming in the direction of the conductor and also in the direction of the electric current. So his left hand will deflect towards the north pole of the magnetic needle, and this rule was given by Ampere's swimming rule. Now that we understood magnetic effects of electric current, let's move on to study the magnetic field due to a straight current carrying conductor. To study this, let's consider a conductor AB. Current flows from A to B. The magnetic field at any point on the conductor is given by the concentric circles drawn at that point. So we all know what is a concentric circle. It has the same center but different radius. And the field lines formed will always be perpendicular to the direction of the flow of current. Now, to study the magnitude of the magnetic field produced due to a straight conductor, we need to consider two factors. The first factor, electric current. I. If I keep increasing the electric current from 2 amperes to 5 amperes, then 10, 15, every time you can see the field produced is stronger and stronger. That is, if the electric current in the conductor increases, the magnetic field keeps increasing, which means the magnetic field is directly proportional to the current flowing in the conductor. B is directly proportional to I. B is magnetic field. And the second factor. Now, to study the second factor, let's consider 2 points P, Q. The magnetic field at point P will be greater than the magnetic field at point Q because let's measure the distance from the conductor to point P to be R1, from the conductor to the point Q be R2. If we keep moving away from the conductor, the magnitude of magnetic field keeps decreasing, which means B is proportional to 1 by R, or B is inversely proportional to R. If the distance increases, magnetic field decreases. If the distance decreases, magnetic field increases. Now, let's call this to be equation 1 and this to be equation 2. Now, let's combine 1 and 2. We get B is directly proportional to I by R, or removing the proportionality sign, we get B is equal to mu naught I by 2 pi R. The intensity or the magnitude of magnetic field around a straight conductor is given by mu naught I by 2 pi R, in which I is nothing but the current flowing in the conductor, R is the distance, 2 pi is a constant, and mu naught is the permeability of the medium, which means the ability of the medium to allow the formation of magnetic field lines, and it is given by a constant. Mu naught is the permeability of medium, which is given by mu naught is equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. Now that we understood the magnitude, let's move on to study what is the direction of this magnetic field. Is it clockwise? Is it anti-clockwise? This is given by Maxwell's right-hand thumb rule, which states, imagine holding a conductor in your right hand in such a way that your thumb finger points towards the direction of the electric current. Then the finger's encircling will give you the direction of the magnetic field. Now that we studied the magnetic field due to a straight current carrying conductor, let's move on to study the magnetic field due to a circular loop. For this, let's consider a circular loop, or you can take a straight conductor and bend it in form of a circle. If you observe in the diagram, you can see that it is almost concentric circles at the end. As we keep moving away, the magnetic field lines gets larger and larger. At the center of the loop, it is almost a straight line. The magnetic field at any point in the circular loop, the direction is given by Maxwell's right-hand thumb rule. And also, to talk about the magnitude, let's consider the first factor, that is the electric current. If I increase the current in the circular loop, the magnetic field gets stronger and stronger. Therefore, magnetic field B is directly proportional to I. If the current increases, magnetic field increases. If the current decreases, magnetic field decreases. And the second factor, B, is inversely proportional to R. That is the radius of the loop. If the radius increases, the magnetic field decreases. If the radius decreases, magnetic field increases. And the third factor is the number of turns. That is, it is not compulsory that I have to use only one circular loop. I can use n number of circular loops. If I increase the number of loops, the magnetic field increases. Now, combining 1, 2 and 3 together, I can write as B is directly proportional to Ni by R. Simplifying this, I get B is equal to mu naught Ni by 2R. This is the formula for the magnitude of magnetic field due to a circular loop. And also, like I told you before, the direction at any point is given by Maxwell's right-hand thumb rule. Now that we understood the magnetic field due to a circular loop, let's move on to our next topic, the magnetic field due to a solenoid. Before we understand how the magnetic field looks like or what is the magnitude or direction, let's see what a solenoid is. A coil of many circular turns of insulated copper wire wrapped closely in form of a cylinder. That is, let me consider a diagram here. I've taken the copper wire and I've wound it closely on a cylinder. And this forms a solenoid. And when I pass the current through these copper wires, they produce magnetic field. And the magnetic field lines look like they start at one end and stop at the other end. But inside the solenoid, they are straight lines. If you observe the diagram closely, it is similar to a bar magnet. In a bar magnet, it starts from the North Pole and ends at the South Pole. Inside the magnet, the field line starts from the south and ends at the north. It is almost similar to a bar magnet, and also it acts like a magnet. And the magnetic field strength at each point in a solenoid is uniform. At every point, it has a uniform magnetic field. And to talk about the magnitude, let's consider the first factor. If I increase the current through the copper wire, the magnetic field gets stronger and stronger. And the second factor, if I increase the number of turns in the coil, if I do more turns, the magnetic field keeps increasing because the current through the copper wires keep increasing. So it is directly proportional to N. So combining these two together, I can write it as B is directly proportional to Ni. Or removing the proportionality sign, I can write it as B is equal to mu naught Ni. And this is the magnitude of the magnetic field produced due to the current flowing in a solenoid. We all know that B is the magnetic field. Mu naught is the permeability, which is given by 4 pi into 10 to the power minus 7 Tesla meter per ampere. And N is the number of turns on the cylindrical coil, and I is the current flowing through the solenoid. Now we understood what a solenoid is and how the magnetic field lines look. Now, one of the main application of a solenoid is an electromagnet. In our previous years, we have studied what an electromagnet is. It is a temporary magnet we can magnetize and demagnetize according to our wish. So, let's see how an electromagnet is formed. A strong magnetic field produced inside a solenoid can be used to magnetize materials like soft iron when placed inside the coil. That is, consider a piece of soft iron and take the insulated copper wire and wind it around it. And pass the current through these copper wires. When you pass the current through the copper wires, it produces magnetic field, and that magnetic field has a ability to magnetize this iron core. And hence it behaves as a temporary magnet. Electromagnets are of wide application. It is used in electric motors, electric generators, electric belts, and hence it is important for us to know what an electromagnet is. Now let's move on to our next topic, that is the force on a moving charge in a magnetic field. The magnitude of Fb, that is the force experienced by the charge when kept in magnetic field, is directly proportional to the charge, speed of the particle and the intensity of the magnetic field. That is, Fb is directly proportional to Q, that is the charge of the particle, V, speed of the particle, and B, the intensity of the magnetic field. And the second point, the charged particle, when it enters the magnetic field, it makes an angle theta with the magnetic field. The magnetic force acts perpendicular to both V, that is the velocity or speed, and the magnetic field. That is, let me show you a diagram. The green lines indicate the direction of the magnetic field, and the magnetic force is Fb, and this is V. Here the magnetic force is perpendicular to B as well as it is perpendicular to the V. Now, if I keep a single charge in the magnetic field, it experiences force. What happens when I keep an entire conductor in the magnetic field? That is given. Let's conduct a small experiment. Here I have kept the conductor between the magnetic field in each case. Now, in the first case, let's consider I is equal to 0. When there is no current flowing through the conductor, there is no deflection in the conductor. But when the current flows from A to B in this direction, you can see the conductor deflects towards the left. Now, when the current is flowing from B to A, the conductor deflects towards the right. So, in each case, here no deflection. Here it deflects towards the left. Here it deflects towards the right. The deflection occurs due to the force acting on the current carrying conductor. The direction is given by Fleming's left hand rule, which states if the forefinger, the second finger and the thumb finger of the left hand are stretched such a way that they are held at right angles to each other, then the forefinger will represent the magnetic field. And your second finger will represent the direction of the electric current. And your thumb will give you the direction of the force acting on the conductor. To demonstrate, consider your thumb finger and your forefinger and your second finger in such a way that they are at right angles to each other. Now, point your forefinger towards the direction of the magnetic field, your second finger towards the direction of the electric current. Then, your thumb finger will give you the direction of the force acting on the conductor. And this is Fleming's left hand rule. Now it's time to understand a different topic, that is electromagnetic induction. So what is electromagnetic induction? To understand this, let me show you a diagram. Now, consider a coil which is connected to a galvanometer. What is a galvanometer? It is a device that is used to detect the presence of the current in a conductor. So, if there is any presence in a coil or a conductor, the galvanometer needle deflects. So, I have considered a bar magnet. Now, take the bar magnet towards the coil. When you keep moving the magnet towards the coil, keeping the coil stationary, you can see there is a deflection in the galvanometer. When the magnet is moving towards the coil, there is a momentary deflection in the galvanometer. This proves that there is a induced current momentarily. So now again, now move the magnet away from the coil. This also induces a current in the coil, and this entire phenomenon is called as electromagnetic induction. The change in the magnetic field induces a current or a EMF, and this current is induced current and the EMF is induced EMF, and the entire phenomenon is called as electromagnetic induction. There are other ways to induce EMF or electric current. Let's see. The first way, consider the magnetic field. You can take a straight conductor. When you move the conductor in the magnetic field, EMF is induced. Whenever you keep moving, as long as you keep moving the conductor in the magnetic field, you keep getting an induced EMF, and that is called as electromagnetic induction. And the second way, consider two coils. But in coil 1 is connected to a battery to send the current through the coil, whereas coil 2 is connected to galvanometer. So, whenever there is a change in current in coil 1, there is a deflection seen in coil 2. That is due to the change in the magnetic flux, which induces an EMF in the coil 2. And another third way to induce electric current or electromagnetic induction in a conductor, again consider the magnetic field and the conductor. Here, keep rotating it about the axis. Keep rotating the conductor in the magnetic field about its axis. As long as you keep rotating it, there is EMF induced every time. and this phenomenon is known as electromagnetic induction. So what is the direction of this induced current or induced EMF? That is given by Fleming's right hand rule, which states that if your forefinger and your second finger and your thumb of your right hand are placed at right angles to each other, then the forefinger represents magnetic field and your second finger in such a way that it indicates the direction of induced current, and the thumb will indicate the direction of motion of the conductor. To demonstrate, take the thumb and your forefinger and your second finger of your right hand, hold it at right angle to each other in such a way that your forefinger is pointing towards the direction of magnetic field, your thumb finger is pointing towards the direction of the moment of the conductor or the motion of the conductor. Then your second finger will give you the direction of the induced current, and this is called as Fleming's right hand rule. In this session, we studied about the introduction of this chapter, what magnetic field is and what are the properties of magnetic field and the units of magnetic field intensity. Later, we studied magnetic field due to current carrying conductor, which included the magnetic field due to a straight conductor, magnetic field due to a circular loop, magnetic field due to a solenoid. Later, we studied the force acting on a charge when placed in the magnetic field and a conductor placed in a magnetic field. And later we moved on to the last part of this chapter, that is electromagnetic induction. In electromagnetic induction, we studied various ways how we can induce a EMF in the coil.